Hello guys, in this video I'm going to show you how to solve minimum height trees. So we're given an undirected graph that has characteristics of k-array tree. In such a graph, we can choose any node as a root to make a k-array tree. The root with minimum height will be called minimum height tree. There can be multiple minimum height trees for a graph. In this problem, we need to find all those roots which give us minimum height trees. Write method to find all minimum height trees of the given graph and return a list of their roots. Okay, a lot of things. So let's go through a concrete example. So undirected graph. For example, let's say I will just flat it out, right? Normally, you you see like tree with mm, parent node, then left child and right child. But this case, because we have an undirected graph, and any node can be a root node, right? Then in this case, I will just flat it out because it hard to make it like a tree with this kind of drawing. So let's say we have three nodes here, right? One is connected to 2, 2 connected to 1 and 3, 3 connected to 2. Okay. So as you can see, in this graph, in this graph, 1 and 3 is kind of the same here because it connected to only uh, one node, right? But 2 here is connected to 2 nodes. So our goals here to find the root node that give us minimum height tree, right? So let's check all the possibilities here. So the first node that we check is node 1. If 1 is a root node, right? If 1 is a root node, then the minimum height will be 3, right? If 1 is a root node, then our tree has 3 layers, right? Okay, let's write down 1 is root node, then height 3. Okay, the next possibility is 2 is root node, right? If 2 is root node, as you can see, left child is 1, right child is 2, is 3, right? Actually, for k-array tree, it can has a mark. It can have a max k children, so we don't have the concept of left and right. Okay, so if 2 is a root node, right, then we have the next layer would be 1 and 3, right? So the height is 2. Okay, 3 is the root node. The case that 3 is the root node is pretty much the same as 1 is the root node, right? 3 is the root node. The next level is 2, and the next level is 1. Then the height is 3. So seems that it seems that the leaf node will never be cannot be cannot give us, sorry, the leaf node cannot give us a minimum height trees in this case, right? 1 and 3 cannot give us minimum height trees. But let's go through another example. 1, 2, 3, 4. Okay. Okay, again we go through the example. If 1 is a root node, then the height is what? Is if 1 is a root node, we have 3 layers, 1, 2, 4, and 1 here is 4. Okay, if 2 is a root node, the height of the tree is, as you can see here, uh, this branch, there are 2 branches from 2 here. The first branch has a height of has a height 2, right? But this branch has a height 3, so in total it will be 3. If 3 is root node, then the height is 3. Pretty much same as 2, not 2 here, right? The height is 3. And if 4 is a root node, then the height is 4. Same as the node 1 here. It's kind of symmetric pattern. Okay. Okay. Once again, the root node, our result, our expected result here should be not 2 and not 3, right? Because it gives us the height of 3, which is minimum amongst all these nodes, right? And once again, node 1 and node 4 cannot give us minimum height trees, right? And you can see 1 and 4 once again the leaf node, right? So the leaf node will not give us minimum height trees. One more example, just one more. Okay, so we're not gonna go into detail like this, but let's see what node will give us minimum height trees, right? Not if node 1 is a root node, then the height will be 5, right? It has 4 layers and 1 is 5, same as node 5, just the other way is symmetric here. So 5 also give us a tree of with height of 5, right? But if it two, there are two branch. Uh, the first branch is this way. It's go down node 1. The second branch will go down node 5, and this will give us higher 4, right? So still better than higher 5, which is leaf node 1 and 5 here. So 2 will give us higher 4, and also 4 will also give us higher 4, because it's symmetric here. 2 and 4 will give the same result. But the best node, the node that will give us minimum height is actually 3. It 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 goes down to 2 branches here. Go to 1 and go to 5, and both these branches will give us height of 3, right? So which is the best in this case. So 3 is root node. Height will be 3. Okay, here the best, the minimum height 3, right? So once again, the leaf node cannot give us the leaf node cannot give us the minimum height 3, right? So the result in this case would be 3. There could be multiple minimum height trees, and in this case we have 2 nodes, 2 and 3. In this case will be 2, right? So it seems like we will gradually, in order to in order to find the root the root node that give us minimum height trees, we could gradually prune the leaf. Like for example, in this case, um, initially it had 2 leaves, which is 1 and 3, which will not give us minimum height tree, so we will prune the leaf. So probably when it ends up with only one node, want to stop here, right? And it is the node that we need, which is 2. In this case, we have initially we have 2 leaf node, which is 1 and 4, and we want to prune those 2 leaves. So 1 and 4 is cut off from the tree, and we are left with 2 and 3, which is also the result. So probably we want to stop pruning the leaf when we only have 2 nodes left, right? 1 or 2 node left, right? Okay. Okay. So the last case, right? Here we have two leaf nodes, which is 1 and 5. Okay, we decide to prune it. So we left with three nodes, which is still greater than 2, right? So we continue to prune the leaves. So in this, currently it has two leaf nodes, which is 2 and 4. So we just prune it. So we left with 3, which is our expected result. So the idea here is that we will gradually prune the leaves until it uh, until we are until we have two node left, two or one node left. So so let's look at our functions. We are given number of vertices and all the edges. Right? Here is undirected graph, right? So in order to do this kind of logics, which is gradually uh, prune the leaves, it seems that we can use topological sort for these kind of operations. As you may remember that in topological sort, we normally require to find a sorted order of um, a sorted order of nodes, right? Uh, so as we find the sorted order, we will it has a step in which we need um, to find the next node, right? That is gonna be cut off from the graph, right? So in this case, uh, we do have to do the same logics here, right? At each step here, we need to cut off the leaf node out of our graph, right? Until the point that uh, our graph left with one or two nodes gonna start. So for topological sort, we need to build our graph first. We need to init graph first. We need to init a incomings. Yeah. Incoming maps. Okay. And next to build graph and incomings. Uh, here we need to, like, after we have graph and incomings, we probably need a queue, we need a queue. In previous program we call it a sources, which is uh, a queue that contains the node that is gonna be a process next, right? So you need a queue containing next node to be processed. In our case, it's probably the leaf node, right? To be from then wanna feed the queue with initial state. Then we start pruning until there is one or two nodes left. Return one or two nodes. Right? Okay. Here is all the steps we need to fill out. Okay. We need a graph, which is in our case, just a map, right? I want to use adjacency list. A map keep records with uh, with a vertex and all the connected vertices, right? Okay, we need incomings. Incomings is just the it's just a map between one vertex and the number of connected vertices. New map. Okay, we need to init a graph, so it probably based on the vertices number of vertices here. So for let vertex of array uh, of vertices here just a integer number, right? It can be 5, so it means our um, our graph will have node from 0 to 4. So in order to access the value from those value, I will use keys method here. So for each vertex, I will feed to the map graph. Right? Graph will set the vertex, and here it will set the destinations vertex, right? Originally it will be an empty array, which means we don't know what are the destination vertices yet. Same for incomings. Initially it will be 0. Let's take a look at the test. Okay, the voice is the next step is to build graph and incomings. So I will run to the edges. For let edge will be the edges will be a list of edge from one node to another node. 0 to 1, 0 to 2, 2 to 3. For example, edges. I will look to the edges, and this structure is each edge into node 1 and node 2. Okay, because it is undirected graph, right? So while building graph, here is just one record will be one vertex with its destinations vertices. So because we have undirected graph, right? So we need to set two-way, right? So we know to set node 1 get node 1 will return to us all the destination node from node 1. Okay? So we will push node 2, and the other way will also be true, which is node 2 give us a list of destination node from node 1. From node 2, I will push in the node 1. For the incoming, let's see, incoming, I will set for node 1 first. The incoming here, for each edge here, I will increment the incoming of the node by 1. So I will need to get the current value of the incomings. Same for node 2 here. Okay. Um, Next step is to init a queue containing next node to be processed, which is also leaves to be pruned. So instead of calling it a queue, let's call it a leaf. We understand that it is a queue, right? That will be processed in 13 first out traverse fashions. We feed the queue initial state, right? So we will add all the leaf nodes to the leaf queue, right? So how we can find the leaf node here? The leaf node is actually the node with has that has only one incoming, right? For in this case, the node 1 has, we will check in the incomings, right? All the node that has the value of 1, like 5 also had one incomings here, but 2 in this case it has 2 incomings, 1 from 1 and 1 from 3, right? So we run to the incoming list, incoming maps for let x of incomings. We need the vertex and number of incomings, so I will accept by the entries method and this structure into vertex and number of incomings. So if number of incomings is 1, I will be pretty sure that this is the leaf nodes, so I will push it to the leaf queue. So we want to start pruning until uh, our number of so how do we know that the number of nodes that has not been pruned yet? So probably we need to keep track of the value, that value, which is node lab, is initially is in number of vertices. So when the node lab is still greater than 2, then we want to keep pruning the leaves here. The next node to be pruned will be all the nodes that in the leaves currently, right? So it means the node lab will be updated and the node labs will be the current node labs minus the amount of nodes inside the leaf nodes, right? Which is the node that will be pruned with these iterations. Leaf dot length probably. Another condition that we want to go here is that we have something in the leaf. Dot length is greater than 0 probably. Okay, we decide to prune this amount, right? So after that I will run through every let's save it here as not to be pruned. Okay, I will process exactly that amount is greater than 0, and each time not to be pruned will be decrement by 1. And inside here, no, because I need the index also. So for I equal to 0, I is less than not to be pruned, I plus plus. Not is leaves at index I. Here is a node, the leaf node, right? And we will by pruning it. By pruning it, it means we need to update our incoming maps, right? So it means that, for example, here node 1 is connected to, we need to find all nodes that is connected to node 1 uh, by using the graph, right? And then we update the incomings here because node 1 is cut off, so it means we need to update the incomings of connected node by decrementing by 1. So neighbor of graph get node. Here's a leaf node. I want to find all its label. Neighbor. Okay. So let's say the nodes in neighbor. I will update the incomings of neighbor. So when the incoming of neighbor reaches reaches 1, uh, that is when it become a new leaf node. So I will push it into push it into the leaf here, but probably we are not doing it right here because here we use a traditional follow, which means we are fixing the index from 0 to this amount, right? And we for each node we will find neighbors and potentially possibly adding new node to the leaf. So it means we're not so for the next probably the next iteration it will be wrong because the index we will start from 0 once again. Here we should actually remove from the queue instead, right? So leave. Here should be the right way. We want to process exactly this amount of node. So for each node, I will ship it from the head of the queue to leave it ship same as DQ, right? And this logic will be the same. So it means for each node, we will process the neighbor and potentially push the neighbor to leave. But that will not affect this processing because we only process exactly this amount of nodes, right? So we will exceed when the number of nodes left is E2 or less, right? So probably here I will return the leaf, right? Why is that? It is because in the last iterations here, in the last iterations, while pruning the leaves here, we will add the connected nodes to the leaf, right? So even after exit here, after exit this loop, the leaves will contain the left node, right? Okay, I think that is it. Let's run the test. Yes, 16. Not sure it will. Hmm. Let's debug it. It's kind of hard to make it run right in the first. Uh, okay. Let's see. Oh, Let's see if it's building graph correctly. 0, 1. It'll be something like 0, 1, 1 to 2, 1 to 3, and 2 to 4. Zero connected to 1, okay. 1 will connected to 0, 2 and 3, okay. 2 its destination will be 1 and 4. 3 its destination will be 1, okay. 4 its destination will be 2, okay. Incoming, let's see. Entry. Oh, probably there's something wrong here. So here we want to the get value and +1. Okay, it works. So that is it for this problem. It's been very long video. So if you're watching us, thank you and see you in the next one.